Hey everyone, welcome to more AP Stats. Today we're going to be looking at 10.3 Day 2. This is our final lesson on the statistical hypothesis testing of a difference of means, or actually a mean of differences. So let's go ahead and take a look at this over here. Suppose that there are 32 seniors who are randomly selected to try both memory strategies. Each student calculated the difference in strategy in number of words, strategy 2 minus strategy 1, and then the differences were x bar diff is 1.5 with a standard deviation of S diff 2.7. So do these data give convincing evidence that the strategy 2 improves memory at the 0.05 significance level? So the first thing that we see as we do this is a 4-part plan. So we're going to be completing this 4-part plan worksheet. Hopefully you guys still have that worksheet that I passed out to you earlier. And yeah, let's just go for it. First of all, the state part is a little bit differently than the way we've been doing it. For parameter, we're just going to define mu diff. So mu diff is a true mean difference in the number of words memorized. Now don't forget, it's the true mean, so you do want to use that verbiage, true mean. Statistic in this case is x bar diff, and that's 1.5 as given in the problem. See if I could highlight that for you. Right there. So that's x bar diff. Next, hypotheses. You know this is always an H0 and an HA. Significance level, we can do that now. That's alpha equals 0.05. But those hypotheses, H0 is mu difference equals 0. That's pretty standard for us. And then alternatively, you have mu diff is greater than 0. Now remember what mu diff greater than 0 means. It means that strategy 2 minus strategy 1 is greater. So strategy 2 has the true mean average greater than true number 1. So those are that. Name of the procedure. This is a 1-sample t-test for mu diff. And then now we've got to check the conditions. So remember, there are 3 that you need to check: random, 10%, and normality. So let's check them all. What's the first one? Random. Is there anything in the reading that suggests that we have a random sample? And yes, if you look at the purple highlights that I may put up there, we see that 32 seniors were randomly selected. Okay, how about the 10% rule? What is 10 times 32? I think that's 320. So do we have more than 320 seniors? And actually, this is one place where the 10% rule is not necessary, because we know that the amount of words that a senior can memorize is going to be independent from senior to senior. So since independence is already taken care of, our 10% rule is not needed in this case. Now, this is a very special circumstance, but if you can guarantee independence, your 10% rule is not needed. So next, how about your normal condition? Which normal condition will hold? Is this a normal population? Is there anything that says that the differences will follow a normal distribution? And no, there isn't. If failing that, do we have a large sample? Now remember, this is a 1-sample t-test, so there is only 1 sample that we need to worry about. How many are in our sample? 32. So under the central limit theorem, the sampling distribution will be approximately normal. There we go. N is equals to 32, which is greater than 30. Therefore, the CLT will hold true. Let's move on to the do section. Here we have fields to fill in here. We have the mean, standard deviation, general formula, picture, specific formula, work, test statistic, and p-value. I admit that's a whole lot for us to deal with. Let's start one at a time. The mean, and that is from the null hypothesis. So this is from H0. So mu diff equals 0. What about the standard deviation? Could they possibly mean 32? I mean 2.7? No, they don't. 2.7 is the standard deviation of the sample, but we're looking for the standard deviation of the sampling distribution. So if you think back, that's going to be S over square root n. So here we go. Standard deviation is S diff over square root n, which is 2.7 over root 32, which we're estimating at 4.77. Next two things you're going to work on: specific formula, and then general formula, then specific formula, and then your picture. So that's three things. I know I said two. Three things: general formula, specific formula, picture. Let's get that done. So here we go, all nice and typed out. T-stat, test stat, is stat minus null over the standard deviation. Specifically, our test stat is T, our stat is X bar diff, and our null is mu diff, which is 0, divided by S diff over square root n. Now we know a little bit about the way those things work, so let's take a look at the picture. Notice the center of this normal distribution. It's actually a t distribution, but close enough. The center of that normal distribution is 0. There's the letters T31 to let the reader know that you're looking at a t-curve with 31 degrees of freedom. And then we locate where is 1.5 in relation to that 0. Where is our statistic in relation to our mu diff? All right, so now that we have all of those in place, all we have to do is substitute all the numbers into the specific formula, calculate the test statistic, and then calculate the p-value from there. There we go. T is equal to 1.5 minus 0 over 0.4773. I calculated that last digit there just to save myself a little bit of sanity. The test statistic, therefore, is 3.143. I've written the p-value out in a couple of different ways. The first way is in probability notation. P of t greater than 3.143. And then I said that's equal to, and then in modified calculator notation, TCDF, lower is 3.143, upper is infinity, and the degree of freedom is 31. Both of those things arrive us at a p-value of 0.0018. And now the big question, is that less than alpha? And I believe so. That number is less than a 0.05. So since we have a p-value that's smaller than alpha, we have support for the alternative hypothesis. So since the p-value 0.001 is less than alpha 0.05, the data supports that the true difference in scores is greater than 0. So that takes us through all of our four-step plan, and the next thing for us to do is your important idea box. Let's go ahead and fill that out for you. So for learning target 1, we've got the one sample t-test for mu diff. And for mu diff, you know that t equals x bar diff minus mu diff over s diff over square root of n. So in essence, this is a one sample test. Now, what's the difference between the two? Well, that brings us nicely to learning target 2. What is the difference? Well, when you have a one sample, like we have in this section, we're basically coming out of a matched pair design, which means that we're going to subtract before and after, or left boot and right boot, or two things that have been matched equally, where one of the things gets treatment 1, the other one gets treatment 2. So we're going to subtract, and then we're going to take an average of those differences. When you do that, you create only one mean, and therefore it looks like a one sample t-test. If you're going to have two samples, that means you're going to have two distinct groups and two means. So the easiest way to see this is if perhaps you have one group with 32 in the sample, and the other sample has, 35. Basically, the two samples are not the same size. If they were the same size, then you would think about subtracting them. But if they're not the same size, then you probably aren't going to think about subtracting measurements from one to the other. So in that case, you would take the average from sample 1, average of sample 2, and then subtract the averages. So it's a difference of averaging the subtractions or subtracting the averages. I know, just let that sink in your head for a second. Let's read through these, check your understandings. In each of the following settings, decide whether you should use a two-sample t procedure or perform an inference about the difference of means, or paired t procedures to perform the inference. Explain your choice. Before exiting water, scuba divers remove their fins. A maker of scuba equipment advertises a new style of fin that's supposed to be faster than to remove. A consumer advocacy group suspects that the time to remove the new fins may be no different than the time required to remove the old fins on average. 20 experienced scuba divers are recruited to test the new fins. Each diver flips a coin to determine if they wear the new fin on the left foot or the new fin on the right foot. Or, yeah. The time to remove each type of fin is then recorded for each diver. So what do we think? Is this a paired procedure or is this a two-sample procedure? And based on the fact that you're getting data paired, basically the pair is the diver's left foot and then the diver's right foot, this looks like it's going to be paired T procedures. This data comes from two measurements from the same diver, indicating that these are paired differences. So paired procedures, you would use mu diff. Okay, let's keep on going. To study the health of aquatic life, scientists gathered a random sample of 60 white piranha fish from a tributary of the Amazon River during 1 year. The average length of the fish was compared to a random sample of 82 white piranha from the same tributary a decade earlier. So what do you think? Do we have one sample or two samples? Well, it seems like it's two samples because they were about 10 years apart, right? And nearly a decade ago. So they're 10 years apart. That seems like it would be two different samples. Let's just make sure they're not pairing. So they're not saying one white piranha from that tributary is equivalent to another white piranha 10 years later. And they're not. Also, the all-important tell that I've been saying, there are 60 piranha in the second sample, and 82 piranha in the second sample. Or, no, the first sample. Yeah, the 82 were first. So, two sample T procedures. The data came from two different samples of piranha. Great. Now, how about this last one? Can a wetsuit deter shark attacks? A researcher has designed a new wetsuit with color variations that are suspected to deter shark attacks. By the way, I don't want to be a part of this sample. To test this idea, she fills 2 identical drums with bait and covers one in the standard black neoprene wetsuit and the other in the new suit. After a period of 1 week, she selects 16 2-hour time periods and randomly assigns 8 of them to the drum with the black wetsuit. The other 8 are assigned to the drum with the new suit. During each time period, the appropriate drum is submerged in the water that sharks frequent, and the number of times a shark bites the drum is recorded. Whoa. So, what do you think? What are the experimental units in this case? Are they actually the wetsuits? And in this case, it's kind of like the drum that is covered with that wetsuit is the experimental unit here. Are we pairing experimental units? Well, no. And that's not even right too. The real experimental unit here is the 2-hour, is the 8-hour time periods. So yeah, we're not really pairing the data here. So this looks like it's a 2-sample T. So the data comes from 2 groups of 8 time periods from each drum. There's no evidence that we're going to directly compare one time period with another time period. So without any evidence of that pairing of time periods, then this isn't a paired procedure. So that's it, everyone. We're done with our day 2 of 10.3, and it's time to start getting ready for a test now, don't you think? I'll see you guys next time.